Hey guys, Mr. O'Sullivan here. Hey, we're going to take a look at homework problem AB number 3. And before we dive into that, again, a quick thanks to Jeff Osborne, AP Calculus teacher at Central Columbia High School in Bloomsburg, PA. Again, shout out to Mr. Osborne for putting together this awesome problem. All right, let's dive in. Diving in. Okay, it's a differential equation problem. And differential equations dy dx is equal to 2xy squared. And we're asked to do, the first thing we're asked to do is sketch the slope field at the 15 points indicated on the graph. Holy buckets, 15 points. What are we doing? That seems like a lot. Usually it seems like we got to, sketch 8 points or something like that. We've got 15. But before we get our knickers in a knot, let's check it out. If we think about it, looking at the differential equation, 2xy squared, well, that means that when x is 0, dy dx is going to be equal to 0. Also, when y is 0. Okay, so in both of those cases, that's going to lead to dy dx, our differential equation, being equal to 0. So that means any point on the x-axis or the y-axis, the tangent line is going to have a slope of 0. So really, if I look at the y-axis, slope is 0, slope is 0, slope is 0, slope is 0, slope is 0. And then I got a couple more points on the x-axis here and here. Those tangent lines have slopes of 0. Well, that's great. Now I'm just down to 2, 4, 6, 8. The 8 remaining points, I'm nearly halfway done. Okay. Well, and we can even kind of, work smart on these 8 remaining points and kind of take a look at maybe some symmetry and not have to do 8 points individually here. Okay, if I look at that point right there, has the coordinates 1, 1. So if I drop that into my differential equation, that means that dy dx is equal to 2 times 1, my x-coordinate, times 1 squared, my y-coordinate, and so that's going to be 2. So that point right there needs to have a slope of positive 2, that tangent line. Okay? If I go to the one right above it, that has the coordinates 1, 2. And again, drop it into my differential equation, that's going to be 2 times 1 times 2, the y-coordinate squared, which is going to be 8. So that one has to have a slope of 8. I'm going to say that line right there has a slope of positive 8. Okay? All right, if I drop down below the x-axis into quadrant 4, but think about it. Look at this point right here, coordinates 1, negative 1. Drop that in, I'm going to get 2 times 1 times negative 1 squared. Well, negative 1 squared, since I'm squaring that y-coordinate, I'm going to get the same result as when that y-coordinate was positive. So again, similar to what I had above at the point 1, 1, at this point down here, I'm also going to have a tangent line that has a slope of 2. So I'm going to have that one needs to be parallel to that, like something like that. Hey, would you believe this point right here at 1, negative 2? You got it. It's going to have a slope of 8, just like that corresponding point up above. So I'm just going to draw that one, sketch it. Again, these don't need to be, exact, but that's close enough for government work. Okay, jump over here to the other side. This point, I like to write my coordinates so I don't make an easy mistake. Coordinates at that point, negative 1, 2. Drop it into my differential equation. 2 times negative 1, my x-coordinate, times 2 squared, square the y-coordinate. That's going to be negative 8. All right, so, okay. Well, that's positive 8 right across the way there. And that, I'm going to call that negative 8. Okay. Would you believe the one right below it is going to have a slope of negative 2? Okay. And then these two down below are going to be the exact same as what I'm looking at on that side. So this one right here is going to be negative 2. And then the one right below, the last one at negative 1, negative 2, is also going to have a slope of negative 8. Okay, so there we go. All right, part B, find the second derivative, d2y over dx2 in terms of x and y. Okay, I can't stop until it's in terms of x and y. So I'm going to start out by taking my differential equation dy dx equals 2xy squared. So dy dx equals 2xy squared. Okay, and I want to find the second derivative, so I want to take the derivative with respect to x, the whole shooting match. Left side, that's how I'm going to get that notation for the second derivative, d2y over dx2 is equal to, I'm going to bring this constant straight down, and then I need to recognize xy squared. I have to use the product rule. Okay, so product rule, I'm going to find the derivative of x with respect to x, that's 1 times y squared plus x times the derivative d dx of y squared. That's going to be 2y dy dx. Okay, not done. What I have to do, that would be the second derivative in terms of x and y and dy dx. So what I've got to do is one more substitution. I've got to substitute the 2xy squared in for the dy dx. I'm just going to rewrite that. 2 times y squared plus, just going to bring that 2 out in front, 2xy, and then I'm just substituting in 2x y squared. Okay, and I just substituted in the dy dx there for that. Okay, so that's my second derivative only in terms of x and y. Sweet. Okay, part C, picking up steam. Find the equation of the line tangent. What? Find the equation of a tangent line. Okay, we've done this about 1 billion times now. All right, I love it. So find the equation of the line tangent to the function at the point 1, 2. So I'm busting out point slope form. I can't even remember any other forms of a linear equation other than point slope. x1, I'm going to drop in my point of tangency at 1, 2. It's my POT. So this is going to become y minus 2, my y coordinate, my point of tangency. I'm going to leave some room for my slope times the quantity x minus 1, my x coordinate. Okay, think about it. My slope is going to be equal to dy dx such that x equals 1, y equals 2, right? That's the x and y value of my point of tangency. Okay, so I'm just going to rewrite this. So it's going to be 2 times my x value of 1 times y squared, which is 2 squared. Okay. Gosh, I know I said never simplify, but I just can't resist. So that's going to be 8. So that right there is my slope at that particular point. And that's my equation of a tangent line. All right, so I've done that first part, check. Now I want to use that equation to approximate the value of f at 1.1. Okay, so I'm going to take that, copy, change the color, and now all I'm going to do is I'm going to take and I'm going to substitute in 1.1 for this x right here. Okay, now I do have to do one more thing. Got to add this 2 to the other side because I want that solve for y. So y is going to be equal to 8 times the quantity, 1.1 minus 1 plus 2. Okay, and this is my approximation of f at 1.1. Notice I'm using that approximation symbol right there. Okay, all right, now I got to keep reading. So that was the second part. Now the last part says, is this approximation greater than or less than the actual value of f at 1.1? Okay, well, what I'm going to look at there is the concavity of function f. Well, and what's going to tell me about the concavity of function f? That's right, my second derivative that I found in part B. Okay, so I'm going to take my second derivative, which is 2 times this quantity here. I'm just going to copy this down. So that is my second derivative. That I found in part B. Okay. Now what I'm going to do is I'm going to drop in my x value of 1 and my y value of 2. So I'm just going to rewrite that real quick. So 2 times 2 squared plus 2 times 1 times 2 times a quantity 2 times 1 times 2 squared. Okay, well, I look at this, and again, this is my second derivative, and I can see that is going to be some positive number. All I care about is it positive or is it negative? Well, it's going to be positive, and so because my second derivative is positive, that means I can say, therefore, f is concave up at my point of tangency at 1, 2, and therefore the approximation, well, let's think about it. It's easy to think. If it's concave up, there's f, concave up. And then if I just have a tangent line anywhere on here, the tangent line is going to be less than the actual value. So the approximation is less than what? Than the actual value of f at 1.1. Okay? Not too bad. All right, now we get to the moneymaker. Part D, shake your moneymaker. Find the particular solution y equals f of x to the given differential equation with initial condition f at 1 equals 2, and then use that function to find the value of f at 1.1. Whoa, okay, so we're actually going to find the value, not an approximation, but the actual value of f at 1.1 after we find this particular solution. Sweet. Okay, so I'm going to start with my differential equation. So dy dx is equal to 2x y squared, and I also need to note my initial condition, f at 1 equals 2. I just remind myself that function notation is telling me that when x equals 1, y is equal to 2. Okay, starting with my differential equation. So the first thing I need to do is separate my variables correctly, no pressure. Moving the dx over, and then I'm going to move the y squared over here. So I'm going to get 1 over y squared dy is equal to 2x dx. Okay, so that's my separation of variables. Now I want to integrate both sides. Okay, I'm going to integrate the right side first, build a little confidence. So the integral of 2x is going to be 2x squared over 2. 2's are going to cancel. I'm just going to have x squared, don't forget, plus c is equal to, okay, now on the left side, again, it's not going to have anything to do with natural log, because if you think about it, a rewrite of this could just be the integral of y to the negative 2 dy. Okay, and so it might be a little bit easier to see, all right, well, it's just power rule. So it's going to be y, add 1 to the negative 2, that's going to be negative 1 over 1. Oops. Careful. Over what? Over negative 1. Okay. All right. So now I'm going to go over here. I'm just going to rewrite this. Y to the negative 1 over negative 1 is equal to x squared plus c. I'm going to drop in my initial condition. So on the left side, I'm going to get 2 to the negative first over negative 1 is equal to 1 squared plus c. And that's going to be on the left side, 2 to the negative first. I'm just going to move that 2 down to the denominator. But then I have negative 1, so it's going to be equal to negative 1/2 is equal to 1 squared plus c. So if I subtract 1 from both sides, I have negative 1/2 minus 1 is negative 3/2 is equal to my constant of integration. I'm going to put that in for c. So now I'm just going to rewrite this. Y to the negative first, negative 1 is equal to x squared minus 3/2. Okay. All right. Now I just have to solve for y. Okay. On the left side, I'm just going to rewrite this as negative 1 over y is equal to x squared minus 3/2. Okay. And then I want to divide both sides by negative 1 or multiply by negative 1, whatever you prefer. So I'm going to have 1 over y is equal to 1 over, I'm sorry, getting ahead of myself. All I'm doing is just multiplying both sides by negative 1. So 1 over y is equal to, I'm just flipping the sign, negative x squared plus 3/2. Okay. Now I want to take the reciprocal of both sides. So I'm going to get y on the left side is equal to 1 over negative x squared plus 3/2. Okay? Okay, now that is my particular solution, but now I'm not done. I want to use that function to find the value of f at 1.1. Okay, so I can kind of say this is, call that f of x. And now what I want to do is I want to find f at 1.1. All I'm doing is just substituting 1.1 in for the x. And so I'm going to get 1 over negative 1.1 squared plus 3/2. Okay. And that's a numeric answer. I'm stopping right there, putting my pencil down, moving on, and living my life. Okay. All right, guys. Hope that helps.